The following problems are practice for solving logarithms. So for number 1, we first want to write that as an exponential. So we have x minus 1 equals 3 squared. So x minus 1 equals 9. So x equals 10 would be our answer for x. For number 2, we have log base 2 of 2 to the x plus 3. And since we just have log base 2 of 2, that's essentially going to cancel out, and we're just left with x plus 3. For number 4, we have 4 to the log base 4 of 64. And since the bases are the same, the 4 and the log base 4 cancel out, and we are just left with 64. For number 4, we first need to condense the logarithm before we solve, or before we write it as an exponential. So we'll have the log of x times x minus 9 equals 1. And now we're ready to write it as an exponential. So we'll have x times x minus 9, and that will equal 10 to the first. So if we distribute the x, we will have x squared minus 9x, and we can move the 10 over to the other side. This factors into x minus 10 and x plus 1. So we have two answers. We have x equals 10 and x equals negative 1. And we need to go back and double check to see if any of those are extraneous. And it looks like x equals negative 1 is extraneous, because if we plug it back in, it will make the logarithm go to a negative number, and you cannot take the log of a negative. So our answer is x equals 10. For number 5, we also need to condense the logarithm before we solve it. So we will have log base 6 of 2x minus 3 equals log base 6 of 12 divided by 3. And now that we have a log on both sides with the same base, we can simply cancel out the logs. So we just have 2x minus 3 equals 4. And now we just need to solve it, so we end up with x equals 7/2. And if we plug 7/2 back in, we have a positive number, so it is a good solution. For number 6, again, we need to condense the logarithm before we write it as an exponential. So we'll have log base 3 of x minus 2 times x minus 4 equals 2. And now we're ready to write it as an exponential. So we have x minus 2 times x minus 4 equals 3 squared. And now if we FOIL it out, we have x squared minus 6x plus 8 equals 9, which gives us x squared minus 6x minus 1 equals 0. Now this one unfortunately is not factorable, but we could solve it either using the quadratic formula or putting it into our graphing calculator. You will have problems that are a little bit easier than this to solve on the test, since it will be non-calculator. But I'm actually going to complete the square to get the answer. So I get x equals 3 plus or minus the square root of 10. So my answer that will not be extraneous will be 3 plus the square root of 10, since 3 minus the square root of 10 will be a negative number, and that would make the logarithms negative. For number 7, we see that we have 2 logs on one side and the bases are the same, but before we cancel them, we do need to take the coefficients and move them to the exponents first. Now we can take away the logs. So we have x squared equals 4 to the third. So x squared equals 64. So x would equal plus or minus 8, but negative 8 would be extraneous, so just x equals 8. In number 8, we need to first condense the logarithms. So we have the natural log of x plus 6 divided by 10 equals the natural log of x minus 1 divided by 2. And now that we have one natural log on both sides, we can cancel them. So we're left with x plus 6 over 10 equals x minus 1 over 2. And now we can just cross multiply and solve. So we have 2x plus 12 equals 10x minus 10, which would give us 22 equals 8x. So our final answer is x equals 11/4. We can skip number 9 since we did not go over that one in class. So feel free to skip that one. And I'll come back to number 10, but since I have the space, I'm going to do number 11. Actually, I can do number 10. So for number 10, we want to think about this as factoring the polynomial x squared plus 2x minus 15, since it's in the same pattern. Except instead of factoring it with x's, we're going to factor it with e to the x. So we will have e to the x plus 5 times e to the x minus 3 equals 0. So now we just need to set each factor equal to 0. So e to the x plus 5 equals 0, and e to the x minus 3 equals 0. And just solve each of those e equations. So if we solve the first one, we have e to the x equals negative 5. And then to get rid of the e, we want to take the natural log. Except we cannot take the natural log of a negative number, so this answer would actually be extraneous. For the second one, we have e to the x equals 3. And if we take the natural log, we have x equals the natural log of 3. And that would be our good answer. For number 11, we have the log of x squared equals x minus, or 6 minus x. And since we have a log on both sides with the same base, we just have x squared equals 6 minus x. So now if we get that all onto one side and we factor it, we get two answers. We have x equals negative 3 and x equals 2. And in this case, both answers work, because if I plug a negative 3 in, I get 9 and 9, and if I plug in 2, I get 4 and 4. So both of these answers are good. There are no extraneous answers. For number 12, in order to solve that, we need to get the bases to be the same. So I'm going to change 8 to the 2x to 2 to the third, and that's still raised to the 2x. 1/4, I'm going to change 2 to the negative 2, and that is still raised to the x minus 2. 4, I'm going to change to 2 squared, and that is still raised to the negative x. And 1/2, I'm going to change 2 to the negative 2, and that is raised to the 2 minus x. And so now I'm going to simplify both sides of my equation. So I have 2 to the 6x times 2 to the negative 2x plus 4 equals 2 to the negative 2x times 2 to the negative 4 plus 2x. And now I can add the exponents together. So I have 2 to the 4x plus 4 equals 2 to the negative 4. And now that I have the bases the same and one on each side, I can set the exponents equal to each other. So I have 4x plus 4 equals negative 4. So 4x equals negative 8. So x must equal negative 2. For the following functions, we want to state the domain and the range for each. So since number 13 is a natural log, we cannot take the natural log of any number that is 0 or negative. So the domain will be 0 to infinity. And the range for natural logs or logarithms is always negative infinity to infinity. For number 14, we have an exponential. And exponentials, the domain is always negative infinity to infinity, because we can plug in anything we want to for x, but the range is restricted by the horizontal asymptote. This particular function has a horizontal asymptote at 0, since there is no number in the back, there's no k value. So our range will be from 0 to infinity. 15 is also an exponential, so his domain will be negative infinity to infinity. And he does have a horizontal asymptote at negative 5, since that's the number in the back. So his range will be negative 5 to infinity. Number 16, since we have an x minus 2 inside the parentheses, we would only allowed to be able to plug in numbers bigger than 2, since we can't take the log of a negative. So the domain will be 2 to infinity. And since he's a logarithm, his range will be negative infinity to infinity. 17 is a little bit tricky because we have 2 minus x, which means that we can only plug in numbers that are smaller than 2. So our domain will be negative infinity to 2. And he's a logarithm, so his range is negative infinity to infinity. And we don't have to worry about number 18 since it is a radical function, and you'll only be tested on logarithms and exponentials. Number 19 is a little bit tricky. We have x squared minus 4, and again, we cannot take the log of any number that is negative. So we would be allowed to plug in any number that is bigger than 2. So our domain would be 2 to infinity. But because it's squared, we can also plug in some negative numbers. For example, if you plugged in negative 3, it would be okay because negative 3 squared is 9, and 9 minus 4 is 5. So we can also plug in any number that is smaller than negative 2. And then his range would still be negative infinity to infinity.